Okay, welcome to chemisode number 4 for Unit 1 Chemistry, and this time we're going to introduce the mole and a few other little things. This involves a lot of calculations, so I suggest you go get a calculator to do some work with, and we'll go through what the mole is and how we do some counting in chemistry. So let's go start off with the basics. Alright, we're going to start off with relative isotopic mass. The idea is that atoms are too small to weigh. Alright, atoms are very, very small, very tiny. Okay, you can't just take one atom and weigh it because they're so bloody tiny. You can't see them, you can't weigh them really well. What we do is we compare the weights of atoms to each other. So we get a bunch of atoms, get a bunch of hydrogens, and we say, well, this weighs a certain amount, and we get a bunch of helium, and we go, well, this weighs more than that, so therefore we have a scale that we're kind of building up. We get a relative scale, and that's built around the fact that hydrogen is going to be one atomic mass unit. Everything else is then compared to hydrogen. So we let hydrogen equal 1, and we go and get some helium, and we notice that that weighs 4 times as much as helium. Helium, that weighs 4 times as much as hydrogen. So therefore the helium, we give a mass unit of 4 to. Then we go along and we look at oxygen. Oxygen weighs, it weighs 4 times as much as helium, and it weighs 16 times as much as hydrogen. So therefore that oxygen, that gets an atomic mass unit of 16. And so we build up this thing called the relative isotopic mass. And it's a scale built around the fact that hydrogen is equal to 1. What we then do is we look at, well, you've got isotopes. Isotopes, as you know, are the same element but different number of neutrons, different number of nucleons in there. What we get is different atoms have different numbers of isotopes. So thinking about it, you got lithium. Lithium has 2 isotopes. It has lithium-6 and lithium-7. Right? This is all hanging around in the air, so what we need to do is get a relative mass for that element. We need to take into account all the different isotopes that we have, and what we end up getting is a relative or an average of the mass of each isotope to make the relative average mass for that element. We can't just add them all together and divide by how many we have, because different isotopes are in different abundances. Okay, so what we need to do is take into account the percentage abundance of different isotopes and the relative isotopic mass of those isotopes. We use this formula, so relative atomic mass, the RAM, equals the sum of the percentage multiplied by the relative isotopic mass. Then we divide that through by 100. Let's put this into practice and have a look at some examples. Our first example is this. Oxygen has 3 isotopes. You have oxygen-16 here, oxygen-17 and oxygen-18. Each of these isotopes have a relative atomic mass or relative isotopic mass of these amounts of AMU. And they come in different percentages. Well, the 16 is 99.76% oxygen, right? If you have a jar of oxygen, 99.76% will be this isotope of oxygen. This one is only 0.4%, this one is 0.2%. So what we need to look at is what will our relative atomic mass be, taking into account these percentages and these masses. Just by looking at it, you can see it's going to be around about 16 because the majority is this mass here. So we bang it into our formula anyway. We get the mass times the percentage, add the mass times percentage, add the mass times percentage. Then we divide it through by 100. This gives us a relative atomic mass of 15.999. Alright? Because we've taken into account all of these percentages and all of these masses. Relative atomic mass equals the sum of the percentage times the relative isotopic mass. The second one we're going to look at is silver, and here it is here. Silver comes in 2 styles, comes in 2 different forms of isotope. We have silver 107 and silver 109. And the masses are here for your silvers as well. Percentages are about half and half. 51% is the silver AG 107 and 48.2% is the AG 109. Just by looking at this, we can kind of have an idea about where our relative atomic mass should be. It's going to be halfway, pretty much halfway in between these two masses here. So it should come out at around about 108-ish, give or take. It's a little bit more of this lighter isotope, so therefore it might come out a little bit less than 108. What I'll do is I'll let you do the calculation for this one, so pause it now. In your calculator, do the relative atomic mass is the percentage times the relative isotopic mass, so the percentage times the mass, add the percentage times the mass, then divide it by 100. Let's see what you end up with. This is what you should have got. This is what you should have written down or put into your calculator. And this is your relative atomic mass for silver. It's 107.86 AMU, atomic mass units. These are all, as I said before, in comparison to hydrogen 1 being weighing 1. So therefore, you have relative atomic mass. The next thing is a bit hard because what happens here is pretty easy, just giving percentages, you get in mass. What happens when you get when you have to work out what the percentages are? And some of the questions you might have to do will require you to work out a percentage of them, giving a certain relative atomic mass. So here's a question from the app that Chemisode has. If you don't know, Chemisode also has an iPhone app, an iPad app. If you go into the App Store, you can download this. This is one of the flashcards for it. It's about relative atomic mass. The question is this: the relative atomic mass for chlorine is 35.45. It has two isotopes listed below. Calculate the percentage of each. So here's the mass of each isotope. What is the percentage? This is where it gets a bit tricky, so I'm going to go run through the process for this. Here it is. Lots of working out here. I should have really coloured it and given it in steps, but what we first of all do is let one of the isotopes equal an unknown. So we're going to call it question mark. Probably should have called it X because it's confused a few of my kids, but one is question mark. That means the percentage of this heavier isotope is 100 take away question mark. Okay, so these here are your percentages. This is an unknown percentage. This is 100 take away your unknown percentage. This model only works when you have two unknowns, by the way. Your relative atomic mass then is equal to the mass times the percentage and the mass times the percentage. You get 100 take away that is your percentage. All divided by 100. What we then do to work this out is we just solve for what this unknown value here is. So first thing is to undo the brackets. You get 34.969 question mark plus this times this, which gives you 3,696.6, and then this times the question mark, which is 36.966. Your relative atomic mass is given to you in the question, so therefore that's it there. What we then do is, again, we're just continuing to solve for this question mark. So you collect the like terms together, so you bring these two together and you get this here. Multiply by 100 across and you get 3,544. Sorry, 3,545 there. You then solve for what the question mark is and you work out that it is 75% is this question mark. So therefore, this lighter chlorine, this question mark is 75%. What we then do is look at what this other one is. This is 100 minus whatever this one was. So therefore it's 100 minus 75%. So therefore this is 25%. So the percentage of chlorine that is chlorine 35 is 75%. The percentage of chlorine that is 37 is 25%. And that's how you work out these ones using unknown percentages when you're trying to work out the percentage. First of all, let one equal a question mark, or let one equal x, and the other one will be 100 minus x. And then solve through using your math skills. Next, we're going to look at percentage composition. So I'll pause it there and we'll come back and look at percentage composition. Okay, percentage composition. So this is percentage by mass of how much of a compound is a certain element. So for example, here's a question. What percentage of salt is sodium? You have sodium here, sodium chloride, NaCl. You might be inclined to say, well, look, you've only got two elements here, so the percentage of sodium is 50%, is half sodium. But you'll be wrong. It's not 50% because the two atoms weigh different amounts. Sodium weighs a different amount to chlorine. What we want to do is find out the percentage by mass of sodium in sodium chloride. So what we need to do is get the weight of each element in the compound and then divide it by the full weight of the compound. So we get the weight of sodium, which is 23, divided by the full weight of the compound, which is 23 plus 35.45. And you get this. Multiplied by 100%, of course, because you're getting a percentage. So 23 divided by this times 100% equals 39.3%. You're getting a percentage of an element in a compound by getting the weight of the element in the compound divided by the full weight of that compound multiplied by 100%. Some more examples coming up, and what I might do is I might just leave it to you and get you to pause for 2 seconds, and you can try and work out what the percentage of these underlined compounds are in these underlined elements are in these compounds. So what's the percentage of copper in copper oxide here? What's the percentage of hydrogen in water here? What's the percentage of oxygen in glucose? And what is the percentage of oxygen in magnesium oxide? So pause it now and then have a go at these, restart it and see how you go. Alright, so you're back and let's have a look at how you went with this. The first one is copper oxide. So you get a simple thing, you get the weight of copper and the weight of the copper oxide. So you add the copper and the oxygen together, multiply by 100%, you end up with getting it about 79.77%, which is copper in there by mass. My next one, let's have a look at where that is. It is the water here. Now with the water, this is a bit interesting because you've got two hydrogens in our water. We need to take into account both of those in terms of the mass. So the percentage mass of hydrogen is 1 plus 1, because you've got two hydrogens, divided by 18 here, multiplied by 100%. Now this might have confused you, so you might have got this next one wrong as well. So I might just get you to pause it again and then make sure you've got this glucose one correct, because remember, if you have two, you need to add them together on the top as well. But the percentage of hydrogen in water is 11.11%. So have a go at this one. And you're back, so let's just see how you went on the percentage of oxygen in glucose. You get 16 times 6 as the numerator, and your denominator is simply 6 times 12, because you've got 6 carbons. 12 hydrogens means just 12, and 6 times 6 oxygens, which is 60 times 16. Divided it through, you get the fact that in glucose, 53.33% is oxygen. And that's how you get percentage composition there. And lastly, really easy one, magnesium, how much is oxygen? Magnesium oxide, sorry, how much is oxygen? 16 divided by the molar mass of magnesium oxide is 39.70% oxygen. And therefore we have percentage composition. Probably the easiest part of this whole thing, getting just a percentage of an element in a compound. Let's have a look at what we've got next. Alright, up next we introduce you to the mole. So let's go have a look at what the mole actually is. Alright, mole. Mole, the mole. What is the mole and how do we use the mole? How many times can I say mole in this video? Atoms are small and they're very, very hard to count. So what we use, we count them in groups. Just like a dozen is 12 and one pair is 2, the mole is 6.02 times 10 to the power of 23, which is a bloody big number of something. It's this amount. Because atoms are so small, we can't count them in individual atoms. We use the mole. The mole is an amount of something. It's how much we use, how much we have, or whatever. To give you a bit more of a perception of this, let's have a look at the next slide. We have a dozen bikes means you have 12 frames and 24 tires. Okay, because a dozen means 12. A dozen faces. In a dozen faces, you have 48 ears. Or sorry, 2 dozen faces, you have 48 ears and 48 eyes. In 3 pairs of gloves, you've got 30 fingers and 6 palms. Alright? So these are looking at amounts of stuff. You're just looking at amounts, groups of amounts. 1 mole of carbon dioxide means you have 6.02 times 10 to the power of 23 carbon atoms, and 1.204 times 10 to the power of 24 oxygen atoms. Because remember, 1 mole is 6.02. Because carbon dioxide is CO2, just like in your dozen bikes, you've got 1 frame, and just as in a bike, you've got 1 frame, 2 tires. In carbon dioxide, you've got 1 carbon and 2 oxygens. So you're counting in amounts of things. Alright, so the mole is an amount of something. We can use this information and kind of go between number of particles, number of molecules, or number of atoms, and convert that into number of mole based around this thing here, this number which is known as Avogadro's number. Let's go and have a look at him. This is the first equation in the mole that you're going to need to really remember. It's N equals capital N divided by capital Na, which means number of moles equals number of particles, that being atoms, molecules, whatever, divided by Avogadro's number. We need to remember this and commit this to memory. We also need to be able to rearrange equations as well, by the way, so just a heads up on that. The question might be, how many molecules are there in 4 moles of methane? How do I go about this? The same steps I'll take in every type of calculation that I do in chemistry. We'll start off with writing down what I know. I'll start off by writing down what N equals, what capital N equals, and what capital Na equals. Little n is the number of moles. So my calculation, or my question here, tells me I have 4 moles of methane. So my little n is 4. My capital N, my number of particles, is my number of molecules. So how many individual molecules? This is a question mark, because we don't know what it is. Na, which is Avogadro's number, is always 6.02 times 10 to the power of 23. No matter what you do, it's always, Avogadro's number does not change, it's always 6.02 times 10 to the power of 23. That's the way it works. So, looking at this, let's do the next step, which is write down my equation I'm going to use. N, we will rearrange this to get N equals, capital N equals number of moles times Avogadro's number, and substitute in our values. Capital N equals 4 times 6.02 times 10 to the power of 23, which ends up being approximately 2.4, or 2. Give or take, times 10 to the power of 24. So therefore you have the simple method of using the moles to go between, using this equation, to go between moles and number of particles. Each time, write down what you know. Write down what each thing relates to. N is number of moles. Do I know my number of moles? Look at my question. Capital N, number of particles. Do I know it, or am I trying to find it like I was in this question? And Na is Avogadro's number. Does not change. It's the same. Always the same. So let's move on. Molar mass. This is probably the most important part of the mole, is understanding what molar mass is and how you can use it properly. The mass number on the periodic table refers to how much 1 mole of substance weighs. You know how many particles are there, but the mass number, that actually gives you an indication of the molar mass, how much 1 mole weighs. So if you go look at your periodic table, you'll see you have carbon. Its mass number is 12, or give or take 12.001 or something like that. That means 1 mole of carbon weighs 12 grams. Magnesium, its mass number, 24.3 grams. So 1 mole of magnesium weighs that much. To get the molecular mass of a compound, add up the mass of each atom in the compound. For instance, 1 mole of methane will weigh 16 grams because you got 1 carbon and 4 hydrogens. So you get 12 plus 1 plus 1 plus 1 plus 1 because 12 is what a carbon weighs and a hydrogen weighs 1. So therefore you get your overall mass of 16 grams. 1 mole of water, it will weigh 18 grams because 1, because you've got 2 hydrogens, and 16, 1 oxygen. You get 18 grams. So that's a molar mass. So you're looking at molar mass tells you how much 1 mole of something weighs. We can use this information and go between and use grams or weigh grams of atoms, and we can work out how many moles of something we have. So really what we can do is count using mass. And here's the example of how we do that. We have converting between mass and mole. Once again, N is our number of mole, M is our mass of substance, and MR is our molar mass. Here's a question. How many mole, it should have many mole, of water is there in a 250 gram cup of water? I take the same steps as I did with the first lot of questions. I write down the stuff I'm interested in. What's my number of mole? What's my N? I don't know that. That's what the question's asking me. What's my mass? My mass always has to be in grams as well, by the way. So it has to be 250 grams. What's my molar mass? My molar mass is 18 grams per mole because it's water, 2 hydrogens, 1 oxygen, and then you get your molar mass there. This here is your equation to convert between mass and mole. This is the golden equation here. This is what you're going to use the majority of your chemistry career. N equals M over MR. It's a brilliant little formula. You need to commit that to memory. So your mass is 250 grams, your molar mass is that. Bang that into your equation and you get how many moles are in a cup of water. It's 13.89 moles of water molecules. Okay, so therefore you get how many, convert between mole and mass. Next question. How many mole are in 3 grams of oxygen gas? How many moles of oxygen molecules? So, what do? Same thing. We always write down what our question gives us. Our question gives us this. We don't know the number of moles. We know our mass is 3 grams. We know our molar mass is 32 grams per mole because oxygen gas is O2. So O2 is oxygen gas, so therefore it's that. What we do, write down our golden rule, our golden equation. N equals M over MR. Bang our things in there and we get in 3 grams of oxygen gas, there are only 0.0937 moles of oxygen. Right? It's an amount of oxygen. It's how many moles there are of oxygen. Alright, so that's converting between mass and mole. I think I've got another one here. Alright, pause this, you can have a go at this. The first part's already been done for you, writing down what you know. But just write down your equation. This one, you're actually going to need to rearrange the equation, so it's going to be a bit harder for you. But have a go anyway. Pause it, write down how do you think you're going to do this question. And you're back, and let's have a look how we actually do it. We write down our formula, N equals M over MR. Okay, number of moles equals mass divided by molar mass. What are we looking for? We're looking for the mass. We need to rearrange this equation to make the M the subject. So how are we going to do that? This. Mass equals number of moles times molar mass. We simply multiply both sides by MR. Just rearranging of equations. So, therefore, we bang our things in. We get 5 times 23 because our moles was 5. Our molar mass is 23 because sodium is 23. And we get 115 grams is how much 5 moles of sodium will weigh. Alright? It's just simply using this equation, rearranging it if you need to, remembering to write down all the stuff that the question gives you. Ah, got even another one. Awesome. How much would 1 mole of sodium atoms weigh? Sorry, how many mole of sodium atoms are there in 1 gram of sodium? Should read the question properly. Information is here. Pause it, have a go, and we'll start again soon. Yep, we're back and we've got our answer. Number of moles equals mass over molar mass. Always, number of moles equals mass over molar mass. Write down your information. Substitute your information in and you get number of moles in 1 gram of sodium is only 0.043 moles. So such a small amount in 1 gram of sodium. There is the answer and there is the mole, converting between mass and mole. This is not hard, it's pretty easy, but sometimes you need to think a bit more. And we're going to go and look at why you need to think a bit more in a second. So let's go have a look at why you need to think a bit more. The reason you need to think a bit more is sometimes they ask you for parts of molecules or parts of atoms, and you need to define what a particle actually is. Molecules are atoms which are joined together, compounds joined together, all right? Elements joined together. Atoms are just the single ones. So within this molecule of water, you have 3 atoms. You have hydrogen, oxygen, and hydrogen. Formula units are things like ionic compounds, which we'll learn a bit more about later on. But they are things that repeat again. So sodium chloride is a formula unit. It's like a compound, really. Well, it is a compound, but it's like a molecule, but not really. So formula units, things joined together. Ions are separate parts of the formula unit. So you'll learn a bit more about this later on when we go and do ionic bonding, but just have an understanding about what each of these particles might mean. Another example, molecules, NH3. All right, ammonia is a molecule. From this molecule, you have different atoms in there. You have N is just a plain atom by itself. Formula units, magnesium sulfate, okay, MgSO4, is a formula unit. And then your ion could be magnesium 2+, but sulfate here is an ion as well. It's a group of elements joined together with a charge on it. So things like sulfate are ions, things like carbonates are ions, nitrates, they're ions as well. But once again, these two things here, going to confuse you a little bit perhaps, but we'll see, I think you'll be alright with it. This is when it gets tricky. So let's go have a look at a question that has become a bit tricky. Calculate. A handful of salt weighs 40 grams. We need to calculate the number of moles of salt in this 40 grams. Calculate the number of atoms, moles of atoms in this 40 grams. Calculate the number of moles of sodium in there, and then calculate the number of chlorine ions in there. So first of all, it's pretty easy. You've got 40 grams of salt. You need to find the number of moles of salt. Simple as that. N equals M over MR. You get 0.68 mole of salt. Done. When we get to number of moles of atoms though, this is how many sodium chloride you have. In sodium chloride, there are 2 atoms. So what we need to do is multiply this by 2, because with every 1 salt, you get 2 atoms. So 1 salt, 2 atoms, so therefore this much salt, you get twice as many atoms. All right? This is where it gets tricky, because you have to think about it for a bit. The number of moles of sodium. We look at sodium chloride, and we go, right, 1 salt, 1 sodium. Therefore, we have this many sodium chlorides, we have this many sodiums. All right, 1 to 1 equals 1 to 1. 0.68 to 0.68. Next one, 1 mole of chlorine, 1 mole of salt means 1 chlorine. So therefore, in this many salts, you have this much chlorine. Pretty simple. But what we want to know is how many chlorine ions there are. So we need to calculate capital N, because it's not asking for the moles of chlorine ions, it's asking for the number of chlorine ions. So we have to multiply the number of mole of chlorine by Avogadro's number, and therefore we get how many chlorine ions there are in this much salt. Let's see if I've got another example or what are we going on. Yep, got another one, which is really good. Calculate the number of hydrogens in 2 grams of sulfuric acid. We've got sulfuric acid here. We want to know how much hydrogen there is in there. How do we do that? First, we need to know how many sulfuric acids we have. So, number of moles equals mole mass over molar mass. So 2 divided by our molar mass of sulfuric acid equals 0.0204 moles of sulfuric acid. This is moles of sulfuric acid. We need to go there first of all. Okay? Because our 2 grams is pure sulfuric acid, we have to find the moles of sulfuric acid first. Once we've found the moles of sulfuric acid, what we then need to do is find out how many hydrogens we have. Now, in 1 sulfuric acid, there are 2 hydrogens. So therefore, in this many sulfuric acids, there are twice as many hydrogens. So that's where it gets a bit tricky, trying to understand exactly where we go. The first thing you need to do, though, is work out the number of moles of what you have, the whole thing, and then work out how much of that is hydrogen, multiply it by the factor that you need. It's a 1 to 2 ratio, so it needs to have double the amount of sulfuric acid that you have. Hopefully that makes a bit of sense. It's relatively complicated and it requires a bit of thinking, but I think, as I said before, you'll be fine with it. We'll move on to the next part, which is empirical formula. So I'll take a break, I'll pause this, and I'll start again with empirical formula. Alright, now we have empirical formula. So this is the last part of this podcast, this video. So we'll go through and try and get this done, and then, yeah, you'll know everything about the mole. Not everything, but you'll know some of it anyway. The empirical formula is the lowest whole number ratio of atoms within a molecule. The idea is that molecules made up of atoms. When we want to analyze things, sometimes we only want to know just the basic idea of what a molecule contains, or what the basic bare bones structure of a molecule is. If we look at these molecules here, we've got some which are empirical formulas and some which are not. We look at water. This is a ratio of 2 hydrogens to 1 water. This is the lowest whole number ratio that we can get here, 2 to 1. So therefore, this is an empirical formula. However, hydrogen peroxide here, H2O2, is not in the lowest whole number ratio between these atoms in a molecule. 2 to 2 is not 1 to 1. Okay? So this is not an empirical formula. We can cancel this down, this ratio down, and it can get smaller and smaller until it gets to the empirical formula. The empirical formula for hydrogen peroxide would be HO, because you have 1 to 1 as its basic ratio. Propene, a ratio of 3 to 6. This can also be cancelled down. If we divide both of these numbers by 3, we get 1 to 2, which is what the empirical formula for propene would be. This is not an empirical formula because it can be cancelled down. The empirical formula for propene would be CH2. Sodium oxide, on the other hand, is a 2 to 1, lowest whole number ratio, all good. Aluminium oxide, 2 to 3, lowest whole number ratio you can get. You can't get any smaller than 2 to 3. Methane, 1 to 4, once again, whole number ratio. Glucose, 6, 12, 6, not an empirical formula. It is not an empirical formula because you can cancel these numbers down. You can cancel the 6 down to 1, cancel the 12 down to 2, cancel down the 6 to 1 again. So you'll have CH2O as being the empirical formula for glucose. Salt, on the other hand, 1 to 1, empirical formula, all good. So you get the understanding that empirical formula is the lowest whole number ratio of atoms within a molecule. How do we find the empirical formula? Well, I can go through some hoopla about it, but I'll just give you the basic idea. The method is this. Finding the empirical formula. It's a 4-step process. 1, you need to find the mass of each element. Okay? 2, you need to find the mole of each element. 3, you divide through by the lowest number of mole, and then 4, you'll work out what the lowest whole number ratio is for those elements there. Here's an example. We've got determine the empirical formula for a compound that contains 40% sulfur and 60% oxygen. Step number 1 asks you to find the mass of each element. So let's go and do that. We've got a percentage here. With percentages, what I'm going to assume, or I'm going to let the mass equal 100. If the mass is 100, we have 40 grams of sulfur and 60 grams of oxygen. Basically, when you get percentages, you want to turn the percentages into mass. So therefore, number 1 is find the mass of each element. You've done it there by turning the percentages straight into masses. Number 2 is find the moles of each element, which is pretty simple. Number of moles of sulfur is your mass of sulfur, here, mass of sulfur divided by the molar mass of sulfur, which is 32. And that equals 1.25 mole of sulfur. Oxygen is 3.75 because you got 60 grams of oxygen divided by 16, and you get this idea here. So, there's your number of moles of sulfur, there's your number of moles of oxygen. Step number 3 is divide through by the lowest number of mole. The lowest number of mole is 1.25 here, so therefore we're going to divide this by 1.25 and this by 1.25. Step 3, divide through by the lowest number of mole. What that gives you is 3 to 1. This just happens to be a nice whole number ratio. So that means we have 1 sulfur to every 3 oxygens, which gives us sulfur trioxide as our empirical formula. Simple process. 1. Find the mass of each element. 2. Find the moles of each element. 3. Divide through by the lowest number of mole. And then 4. Get the lowest whole number ratio. Done, diddly-unskies. Pretty simple. Here's the next example. Next example is this. 3 grams of a nitrogen oxide is found to contain 0.912 grams of nitrogen. What is the empirical formula for this oxide? Step 1. Think about it. What was it? Step 1 was find the mass of each element. Now we've got this much nitrogen, 0.912 grams of nitrogen. We've got this much of nitrogen oxide. So therefore, the difference will be our oxygen. So we've got this much nitrogen, this much oxygen. The difference between these two things, between the nitrogen oxide and the nitrogen, will give you how much of this oxygen you have. So therefore, 1, done, you've got our mass of nitrogen and oxygen. Number 2, look back, what was it? Number 2 was finding the number of moles. Number of moles can be done by working out your mass divided by your molar mass. So 0.912 divided by 14 equals 0.65. And then 2.008 divided by 16 gives you 0.1305. Okay, this is your number of moles of each element. So the next step, step number 3, is to find or to divide through by the smallest number of moles. Nitrogen is this, oxygen is this. The smallest is 0.065. So what we need to do is divide through by 0.065 on both of them. Step number 3, done. What that gives you is 1 to 2, a pretty nice even ratio. This comes out as being your ratio, 1 nitrogen, 2 oxygens, gives you NO2, nitrogen dioxide. Pretty simple. Each time following exactly the same steps. Find the mass of each thing. Find the moles of each thing. Divide through by the smallest number. Find the lowest ratio. Now, if this happened to be 2.5, what you'll need to do is multiply through both of these by 2 to get 2 and 5. Okay, so you need to get this last step here to be the lowest whole number ratio, because you can't have 2.5 down in the subscript here. Right? If this happened to be 1.3, you multiply this by 3 and this by 3. So you'll get 4 to 6. All right? But you'll get it. You'll understand that. Summary time. So here is our summary page, and it kind of covers all of what we've done so far and gives you all the formulas and all the methods of how to work out what you need to know. Anyway, starting off with our green here, we've got our relative isotopic mass, relative atomic mass, and relative molecular mass. You should know what each of these things are, okay? Your relative scale is always comparable to a hydrogen atom, which has which is given a value of 1 atomic mass unit, and it's measured in AMU. So all your relative things are comparable to hydrogen being 1 in the AMU scale. Relative atomic mass is equal to the sum of the percentage times the relative isotopic mass divided by 100. This is your RAM equation. So when you're trying to work out and use isotopes to find out the relative atomic mass, you use this equation here, which normally turns out to be a lot bigger because you've got probably about at least two or three isotopes that you're going to average out, and it's using the percentage times the mass, adding them together, then dividing them by 100. The next thing we looked at was percentage composition, and it's looking percentage by mass of composition. So you look at for the mass of the element within the compound, divided by the mass of the overall compound, and then times that by 100%. That one was pretty straightforward, shouldn't really need to go over that again. The mole was interesting. You need to know what molar mass means and the number of moles used to measure and count atoms. Alright, molar mass is the mass of 1 mole of substance, which just so happens to be exactly equal to what's on the periodic table, the molecular weight. Okay, so your molar mass is how much 1 mole weighs, found from the periodic table. These two equations, n equals m over mr, and little n equals capital N over Na, are the two things you need to be able to use and work with. So one's using mass, and one's using number of molecules or particles. Alright, so whenever you're dealing with a mass, you'll start off using this one here. Whenever you're dealing with particles or molecules, you'll probably use this guy here as well. So they're the two differences in there. Once we use that, once we understood the mole a bit, we can work out empirical formulas. And remember, empirical formula was 4 steps. Always these 4 steps. Firstly, find the mass of each element. If it's a percentage, change it into grams. Otherwise, just think about what each element weighs. Second of all, find the number of mole of each of the elements. Thirdly, divide by the lowest number of mole. And lastly, find the lowest whole number ratio for those elements, and then you can put it together as your empirical formula. That's a summary of what we've covered. It doesn't look like much here, but as you can see, this video is bulging at the seams at around about 40-something minutes. Alright, do it in parts, don't do it all at once, but please look over this video again and you'll get an idea of what you need to know and a couple of examples about how to do it. In the description, as you can see, there's little links to each part of this video. There's a link to the relative atomic mass area. There's a link to the percentage composition area. There's a link to the mole area. And there's a link to the empirical formula area. So go find those links and go to those areas if you're having trouble with something. And that's it. Until next time, happy studying chemistry. And if you have any questions, please don't hesitate to ask. Join the Edmodo group. Like the Chemisode on Facebook, and yeah, well, take it easy. See ya.